Hi, and welcome to 15.5 Diffraction, Dispersion, and Doppler Effect. Or as I like to call it, the Triple D lesson for those of you who like the show Diners, Drive-Ins, and Dives. But this is a different type of Triple D. So diffraction is the spreading out of a wave. You're going to see this is diffraction, okay? Dispersion looks like this. That's how you get rainbows. And then Doppler effect, we already kind of talked about. But did you know that instead of just in sound, you could have Doppler effect where something comes towards you and it's a higher pitch and then moves away from you with the lower pitch? That's because of different frequencies. So a higher perceived frequency and then a lower perceived frequency. Well, we've been talking about light and electromagnetic waves that have different frequencies with the electromagnetic spectrum. And you could have Doppler effect with light too. You could have higher perceived frequency of light and then a lower perceived frequency of the light if the source is moving away from you, which is the redshift. I do want to just do this quick thing with diffraction and reflection and refraction. So reflection looks like this. Incident ray, and then it bounces off. So that is the bouncing of a wave. Refraction looks like this with the incident ray, and it is the bending of a wave. So it bends towards the normal in that case. Diffraction, so I should write bending. So reflection is the bouncing, refraction is the bending, and then diffraction looks like this, where there's a barrier, maybe there's an opening or aperture in the barrier, or it could just be like one side of a wall. And instead of using ray diagrams that show the direction of the wave, they'll draw the wave fronts as they approach the barrier. And it's like, well, what's going to happen as the wave fronts go through the barrier? What happens is they diffract or spread out. So you'll have the same wavelength, but they diffract, they spread out beyond the barrier. So you might think, well, if I didn't just draw that there, you might think to yourself, well, there's this barrier here. So it's almost like there's a path and the waves will just look like that. But actually what happens is they spread out past the barrier and you get this spreading out of the wave. So diffraction is the spreading beyond a barrier. Spreading. And now we have like the three different things that waves do. Reflection, refraction, and diffraction. So in the multiple choice questions, they like to take the fact that it looks like this, and then it's actually back to like 14.3. The questions are going to look similar to that where we had wave interference with the constructive and destructive interference at the crests and the troughs, like that. And the cool thing is, with light, if you have a barrier with two openings, the way that we know that light is a wave, because you can't really see, like, can you see light? Like what it actually is? Well, we know it's a wave partially because you get this diffraction pattern through both openings, and this is called the Thomas-Young double slit experiment, 1, 2 slits, and you get areas of constructive interference, and the light is actually more intense at these areas. So you'll get bands of bright light and bands where, so this is destructive interference where the trough meets the crest, and it'll actually be like dark bands. So you'll get an interference pattern that's light, dark, light, dark, light, and then it spreads out, which is not what you would expect. You would expect that if you had these two openings here and you shine light through it, then you would just get two bands of light. But that's actually not what we observe when we do the Thomas-Young double slit experiment. You get areas of constructive and destructive interference because of the spreading out or the diffraction of the light. And that's how we know that light is has wave-like properties, but as we'll discuss in Unit 16, there are experiments that you could do that show that light has particle-like properties, and that's where the particle-wave duality of light comes into play. It's some weird modern physics stuff where light sometimes behaves like a particle and sometimes behaves like a wave, and that's called particle-wave duality. But for now, let's just talk about diffraction in general for light. So number 1 says the diagram below shows a series of straight wave fronts produced in a shallow tank of water approaching a small opening in the barrier. They tell you the wavelength is 1.4 centimeters, and that wavelength isn't going to change just because it goes through the barrier. But it says which diagram represents the appearance of the wave fronts after passing through the opening of the barrier. So we're looking for that diffraction pattern, something where it spreads out and curves around the barrier. It's not going to look like C or D. The two that look like this diagram are A and B. And how do you know which one it is? Well, the wavelength doesn't change just because it diffracts. You're not going to change the wavelength or even the frequency of the wave just because it diffracts. It just changes the shape of the wavefront. So it's choice A, not B, because that's a smaller wavelength. Number 2, a wave of constant wavelength diffracts as it passes through an opening in the barrier. As the size of the opening is increased, the diffraction effects, it actually decreases. So it's not going to diffract as much if it's a wider opening. We didn't talk about that, but there's some videos that show this. You could just think of it as, well, if this is an opening here, wave fronts approach it, it's going to diffract. We know that. Well, if I make this wider, let's see if I can move this. There we go. Let's keep on making it wider and wider and wider. What if it's so wide? Is it going to really diffract as much, or is it pretty much going to look the same? It's going to look the same as it goes through, and maybe at the ends it'll diffract a little bit, but it'll be mostly straight. And I changed the wavelength there, but you get the idea. The point is, the bigger the opening, the less diffraction there's going to be compared to the size of the wavelength. So also the wavelength compared to the opening also has some effect. So as the opening is increased, the diffraction decreases. Number 3. A beam of monochromatic light approaches a barrier having 4 openings of different sizes as shown below. Which opening will cause the greatest diffraction? It's kind of the opposite of number 2. If we want more diffraction, we want a smaller opening. So it's going to be choice A because it has the smallest opening. The smaller the aperture or the opening, the greater the diffraction. Number 4. Parallel wavefronts incident on an opening, that just means they're coming into the opening, in a barrier are diffracted. For which combination of wavelength and size of opening will diffraction effects be the greatest? Well, if we want the diffraction to be great, we said before that we want the opening to be smaller so that the wave spreads out more. If it's super big, the opening, then it's not going to really diffract at all. So we want a narrow opening, so that eliminates B and D. What about the wavelength? So think about this. If you have an opening here, visualize these. Let's say it's a short wavelength. Think of it like they're very energetic here. They're not going to diffract as much. They'll just kind of push through the opening because they're so energetic. So it's not that much diffraction if it's a small wavelength. But if it's a longer wavelength, you could think of it like there's less energy in the wave and it has more of a tendency to bend and spread out because it's not going to like push through it as much. It'll just kind of chill and spread out like that. So it's we want a longer wavelength and a narrow opening, and that'll give us the most diffraction out of those. Actually, I'll keep that. That's kind of a nice diagram. It's overlapping that, but who cares? Number 5. The diagram below represents shallow water waves of constant wavelength passing through 2 small openings, A and B, in a barrier. So this is meant to showcase that Thomas Young double slit experiment, and how, yes, with water waves, you can clearly see it with your eyes that there's going to be this interference pattern. And then when you do the same experiment, but with smaller openings and you shine light through it, you get the same kind of interference pattern instead of just two bands of light. So that's kind of where we're going with this. That's why we're talking about water. It's like, oh, I thought this was the electromagnetic spectrum unit. It comes up again. So which statement best describes the interference at point P? Remembering, this is a reminder, at point P, we have a trough, that's the dotted line, meeting a crest, that's the solid line. So maybe if you looked at it from the side, you would have a trough meeting a crest, and they're coming towards each other. What happens when they interfere? They cancel out, and it's destructive, so it's not constructive. And it says it causes a decrease in amplitude. That's right, because this is the amplitude, right, from equilibrium. And when they cancel out, that decreases the amplitude. The wavelength will stay the same. They just kind of phase through each other. They don't really change each other's wavelength. Again, I'll leave that little drawing there. Number 6, a prism so that was all Doppler effect. Now we're getting into dispersion. A prism disperses white light, forming a spectrum. It kind of looks like this. So white light comes in, it like spreads it out into the different colors of light that make up that white light. The best explanation for this phenomenon is that different frequencies of visible light, they're going to refract differently. So the red light doesn't refract as much as the violet light does. The violet light bends more. Well, if you remember what refraction is all about and why the light bends, the light ends up bending because it slows down through the different medium. So the violet light will slow down more than the red light does when it enters the new medium. Now we're talking about refraction. So it's going to move, the different frequencies move at different speeds, which causes them to refract differently. They're not necessarily reflected inside or absorbed or undergo constructive interference. No, it's all about refraction, and you have to remember, the things refract because they're bending, because they're moving at different speeds. So that's kind of shown here. Which phrase best describes the phenomenon illustrated below? Scattering and diffraction, reflection and interference, transmission and Doppler effect, or refraction and dispersion. So this is a special case of refraction where the white light disperses into different frequencies of light, because all the different frequencies of light refract different amounts. So it kind of spreads it out. It disperses it. Number 8, as viewed from Earth. So now we're getting into Doppler effect. As viewed from Earth, the light from a star has lower frequencies than the light emitted by the star. It's saying like the light is being emitted by the star, but from Earth, the light has a lower frequency than what it is actually emitting. So why would the light from the star come to Earth and have a lower perceived frequency? All right, because of the Doppler effect. So if it has a lower frequency, that means that it's moving away. I'll try to draw, remember this diagram? I'll try to draw better than that. So we had like this, close together, far apart, close together, far apart. And we said that the velocity of the thing was moving this way. So here is high frequency waves, and here is low frequency waves. So if the frequency is lower, that means here's Earth, and the star is moving away from Earth. So that's going to be B. Number 9, astronauts traveling towards Earth in a fast-moving spacecraft receive a radio signal from an antenna on Earth. Compared to the frequency and wavelength of the radio signal emitted by the antenna, the radio signal received by the astronauts has what? So this is another interesting example of how electromagnetic waves, such as radio waves, you can have the Doppler effect with that. So the classic one is something like the redshift, which is number 8. That has to do with visible light. But you could also have this Doppler effect in radio waves. So let's draw Earth. Here's Earth. And Earth is emitting this radio wave to our astronauts. And the waves are all propagating outward like ripples on a pond. So think of that. So frequency is all about how many waves per second. If the astronauts are coming towards Earth in their little spaceship here, all right, they're moving this way. Are they going to hit? So let's say, and then there's another spaceship over here that's just stationary. They're just hanging out. Which will hit more waves per second? Actually, this is not moving anywhere. Which is going to hit more waves per second? This one's just passive. These waves are passing by it. But then this one's moving towards the source. This one will hit more waves per second. And more waves every second means that there's a higher frequency. The waves go by you more frequently. And then they'll also have a perceived, it's going to kind of look like this to them. Since it's a higher frequency, it'll make it seem like the wavelength is shorter than what it actually is. Like this is a longer wavelength, this is a shorter wavelength. So if it's a higher frequency, it's a shorter wavelength, and that's going to be choice C. Okay, so that's the idea there. Number 10 looks like just a review of refraction, because why not? So we're done with the diffraction, dispersion, Doppler effect questions, and then when you're talking electromagnetic waves and you're talking the physics regents, they like these refraction problems. So a ray of monochromatic, that means one color of light, of frequency 5.09 times 10 to the 14 hertz. So that's a hint that we're probably going to have to look at that indices of refraction in our reference table, page 2. It's traveling from water, which if you look in the reference table, has an index of refraction of 1.33. So there's some hidden information there, that number 1.33. We could write that right here. N1 is equal to 1.33. And it's going into medium X. So we don't know what the index of refraction for the second medium is. But we do know the theta 1, the angle of incidence, is 45 degrees. And the angle of refraction, or theta 2, is equal to 29 degrees, as shown. Calculate the absolute index of refraction of medium X. So we're looking for this. So there's my givens. There's my unknown. I'm going to write Snell's law. That's the equation. And I'm going to substitute in, making sure that N1 stays with theta 1. So that's 1.33 sine 4. Make sure you put the 45 with the 1.33. You'll get a different answer if you just mix them up. And then N2 is over here, and that goes along with the 29 degrees. So we'll put 29 degrees. Now make sure your calculator is in degree mode. 1.33 times sine 45 is about 0.94. Make sure you keep that long decimal in your calculator, but you don't have to write the whole thing over here. And then you're just going to do divided by sine 29 in your calculator. Like I said, make sure that you're keeping that big long fraction there. And then you should get N2 is equal to about 1.94 when you round it. So it went from a lower index to a higher index. It bends towards the normal, which is what we would expect if it goes from lower to higher. Okay, so that's 15.5, and that's about it. Have a great day.